Hi. Hello. So, my name is Richard Wilden. I'm the Deputy Head of Department. Thank you for the introduction. On behalf of the department, welcome to this Engineering Horizons session, and thank you for your time today. We've been running the Engineering Horizons series to try and engage with you, the alumni, to tell you a bit more about what's going on in the department, how things might have changed since the time that you're in the department, and also to showcase some of our fantastic research that's going on. I am going to start in a little bit by telling you a bit more about the what's changed in the shape and size of the department, and then we're going to have our main agenda, which is two research talks. I'm now going to ask Emilio if he would like to start his screen sharing, and I'll reintroduce you to one of my colleagues within civil engineering, Professor Emilio Marti nez, who's going to be talking about material degradation across multiple areas. So, Emilia, if you'd like
Thank you
to
very much, Richard, for the kind introduction. I hope everyone is seeing my screen full screen. Good afternoon, everyone. It's really a pleasure to meet you and with interact with you. As you heard, my name is Emilio Marti nez. It's a complicated Spanish name, and I'll tell you a little bit more about myself later. But I'm an associate professor of engineering science here at Oxford, and I work on topics related to the energy transition. So in the UK, like in many other countries, we have a great desire to embrace the energy transition, to transition towards a net zero society. And that brings some engineering challenges. And I'll tell you a little bit of what my research group does in trying to tackle those challenges here in Oxford. Before I get into this, just one slide about myself. As you can probably figure out from my name and my accent, I was not born in Oxford or anywhere nearby. I'm originally from Spain, from a region called Asturias that is here in the north. And it's a very beautiful place. You're all encouraged to visit and travel there if you can. As you can see, we have very nice beaches, cows, mountains, cathedrals. But it's been quite a long time since I don't live there. I moved to the UK. Well, I did my undergrad back in Spain in general engineering, like most of you. And then my PhD took me all over the world, mostly to the Technical University of Denmark, but also Cambridge, UC Santa Barbara, and Luxembourg. And then after my PhD, I stayed in Cambridge as a research fellow. And then I started my academic career at Imperial. And a few years ago, a year and a half ago, actually, after 4 years as an academic at Imperial, I moved to the University of Oxford. Here at Oxford, I lead the Mechanics of Materials Lab. This is a diverse and relatively large group of people. You can see them here. Hopefully, some of you will recognize this pub. It's a classic in the Oxford summer. And you can see a bunch of people here. They're postdocs. It's a group we have now 11 postdocs and 12 PhD students, so it's a relatively large group. People from all over the world. Of course, many are from the UK, but also from continental Europe, Asia, the US, and so on. And what these people do is basically work on tackling engineering problems and typically materials problems that sit at the interface between civil engineering and other disciplines. So this could be solid mechanics, material science, condensed matter physics, chemistry, geology. A lot of these problems are linked by a few things. One of them is their connection to the climate crisis. So we are very interested in tackling problems that are holding back the energy transition. So you can see here in our logo that we care about basically hydrogen technologies, batteries, offshore wind. Also some problems related to that are kind of an outcome of the climate crisis. For example, trying to understand sea level rise. We're developing models that bring more physics into the understanding of sea level rise. We're trying to address the implications of the climate technology. And then we have a website here which you can access, and then you will find a lot of information about us, the people in the group, what we do, the research projects that we have, and so on and so forth. And some of the things that we have as well. So some of our code, some of our resources, and lab resources. Today I want to just give you a snapshot very briefly of some of the activities that we do. It's going to be a bit high level. I hope. I mean, if you have questions, I'm very happy to get more deep into the details, of course, during the Q&A session. But I didn't want to. I know some of you come from very different backgrounds, so I didn't want to give you a very detailed talk. But again, the motivation is always this fight between engineering and climate change, right? And we know that engineers are going to lead the fight against climate change. And there's very big ambitions from all governments around the world. This is some examples from the UK. So the UK has committed to decarbonize the electricity system by 2035 and be fully net zero by 2050. Same goes for the European Union and many other places around the world. So this is a very strong commitment. It's some things are easy to decarbonize, while others are particularly difficult, and it's going to be a challenge. We want to go to zero. We don't want to go to 10%, to 20%. We're going to go all the way to zero. However, I would argue that, engineers have done already quite a great job in stepping up to the challenge and in, addressing the technological answer to climate change. Here, I'm just showing some examples. So on the left, you see the cost of solar energy, so the solar panel per watt, the price of a solar panel per watt. This is the orange curve, and in the blue curve, you see the panel installation. So this is from some years ago, but you already see that, the drop is really remarkable, how much we're lowering this and how much this is going outwards. The same goes for wind energy. Again, for some years ago, this is the cost of wind energy. This is the installation capacity, the global capacity. You can see a remarkable change, a remarkable drop, and a remarkable increase in capacity. And the same goes for batteries. Really very exciting stuff is happening in battery technology, lots of it coming from Oxford. And you can see that we're really approaching our theoretical limits, basically. We're really increasing the batteries to really taking them to the real limit. So it's really quite exciting about this. And when people ask me about what engineers are doing about climate change, I typically point to these graphs because it's really remarkable what engineers have achieved. But the problem is that if you want to achieve these very ambitious goals that the governments have established, this thing needs to keep going down. We would only enable a fully global uptake of the energy transition if we provide technologies that are really competitive without any types of subsidies and so on. So we really need to keep going. We need to keep pushing, and we need to keep increasing that technology. And what I'm interested in particular is the materials problems that are holding back the energy transition. Okay, what can we do from a materials degradation perspective, from an infrastructure perspective that will bring this thing down, this thing down, this thing up? This is the idea. So I'll tell you we work on a number of problems in this regime, but within this realm, but I'll tell you about 3 specific problems. The first one is hydrogen technologies. You've probably seen in the news and so on that hydrogen is going to play a very big role in the energy transition. The jury is still out on how big this role will be, but we know that hydrogen has multiple benefits. One of them is usually called the Swiss knife for decarbonization. It has the potential to decarbonize many applications and sectors, including some that are known to be particularly difficult to decarbonize, such as aviation or steel making. It's difficult to think of alternatives to decarbonize those 2 sectors. So this is part of the picture. If we want to go to fully net zero, there are some areas that's going to be very difficult that we cannot electrify. We cannot put batteries in planes, but hydrogen is going to play that role. So hydrogen is going to be our ally there. So it's going to play a big role. And the other key factor is that this needs to happen quite fast. So we don't have a hydrogen energy infrastructure. This is a new technology. So if we really want to meet that commitment of having all the power system net zero by 2035, or having full net zero society by 2050, we need to urgently deploy this hydrogen infrastructure. And in fact, the European Union is aiming at having 40,000 kilometers of hydrogen transport pipelines in 10 years. And Airbus has said that they will have hydrogen fuel planes in 2035. So again, 10 years from now. So this is going to be quite a remarkable challenge. And also hydrogen can not only play a role in decarbonizing many applications and sectors, but it was also identified as the best solution for large-scale electricity storage. So this was a report that the UK government commissioned to the Royal Society. And as you can see here, the Royal Society concluded that storing hydrogen in solution man salt caverns will be the best way to meet the long-term storage need. Because basically you need to make sure that if you base yourself on renewables, you need to make sure that you accommodate the intermittency of renewables with some sort of large-scale energy storage. And hydrogen will play that role. So it's going to play a role, but at the same time, hydrogen has a dark side. We know since almost 150 years ago that hydrogen makes metals very brittle. This is something that was reported first in the Proceedings of the Royal Society, the oldest scientific journal in the world. This was reported by Johnson, as you can see here, and where he speaks about some remarkable and extraordinary decrease in toughness and breaking strain in iron and steel in the presence of hydrogen. And scientists very rarely use words such as remarkable or extraordinary, particularly in those days, but the way that hydrogen interacts with metals is indeed quite remarkable and extraordinary. You can see some examples here. For example, if you look at the left, this is ductility. So these are stress strain curves. I'm sure when you were students here, you did pencil stress strain curves in the lab. This is part of the second year lab experiments these days. And you take a piece of metal, you expose this piece of metal to hydrogen. Hydrogen can come from a gaseous environment, like in this case, or it can come from water vapor, from the humidity, from seawater in a corrosive environment. But in one way or another, if you introduce hydrogen into your sample, into your metallic sample, and then you do this kind of uniaxial tension test where you pull and measure the stress versus strain, force versus displacement, you see that if you introduce hydrogen into the sample, you very significantly reduce the ductility, the failure strain of those samples. And the effect is even more remarkable if you talk about fracture toughness. Again, those of you who have done their undergrad here will remember those concepts from first year, second year statics and structures courses. We talk about fracture mechanics, fracture toughness. This is the resistance of a material to fracture. You can see that this is a pressure vessel steel, and this is, you can see that it goes all the way from a fracture toughness of 220 megapascal square meter to well below 20 megapascal square meter. And you can see that the quantity here of hydrogen, 6 parts per million, a tiny amount of hydrogen can bring the fracture resistance of a metal an order of magnitude. So basically, you go from something that is very ductile, that you really want to use for your structures, to something that is almost as brittle as an engineering ceramic. So this is a problem, of course. And this is fatigue as well. You may remember that fatigue as well for second year course on statics and structures. This is the crack growth rate, so the crack speed. And you can see here, this is the response in air. This is a log plot, by the way, log plot. So you can see that we increase by more than an order of magnitude the crack speed whenever we expose these pipeline steels to hydrogen gas or any hydrogen-containing environment. So that's a problem because, well, hydrogen is everywhere, first of all. But second of all, we want to store and transport hydrogen gas. This is the key to the energy transition, or this is a key element in the energy transition. But when we do so, our metals are going to become very brittle. And you can see here that the reduction is really dramatic. Very little amount of hydrogen makes orders of magnitude change in fracture and fatigue resistance. So that's a problem, of course, and one that worries a lot of engineers and where I think we can play a role. And in fact, hydrogen, this phenomenon is called hydrogen embrittlement because it makes metals brittle. And this is kind of an old problem. We know this since quite a while ago. It used to be a problem mostly related to very aggressive environments. So this is probably the most famous oil and gas accident in the world, in the Gulf of Mexico, the Thunder Horse accident. And this was due to the failure of a bolt due to hydrogen uptake. So here the hydrogen came from the seawater, from the corrosive reactions, and that made your bolt crack. This is another very classic example, the San Francisco Bay Bridge, which required 45 million of repairing costs. Again, some bolts were exposed to a more humid environment than they were supposed to be. They absorbed hydrogen and then they cracked. And this is from The Guardian a few years ago. This is as you probably remember in your visits to London, the Cheese Grater Tower, one of the most emblematic skyscrapers in London. And you can see that The Guardian talks about this hydrogen embrittlement phenomenon. So bolts were cracking and falling down, and they had to close this building. So this is basically the key takeaway is that this is an old problem. It used to happen in very aggressive environments. We realized that modern high-strength steels are more susceptible to this problem. So now, not only very aggressive environments are an issue, it's an issue for also what you would thought would be very mild environment, like this building over here, right? There's no seawater corrosive environment here. But that mild environment brings enough hydrogen to cause problems in these modern high-strength steels, which are not susceptible. But it's not only a problem, in many applications and sectors, from construction to oil and gas, but of course it's a problem for the energy transition. And we don't still have hydrogen technologies there, right? There's a lot of ambition, there's a lot of commitments from the governments to create a hydrogen economy, but very few countries are coming up with the technology. Norway is one of them, and as you can see, this hydrogen material degradation is already having significant issues. You can see here that there's an explosion in a hydrogen fuel station. So that's an issue. And of course, that's an issue because we need to take decisions quick. So for example, one of the key, I would say, engineering/scientific questions that people are discussing these days is, can we transport hydrogen in the natural gas pipeline infrastructure? Because building new pipelines for hydrogen is going to be 5 to 10 times more expensive. So people are saying, okay, we already have a natural gas pipeline infrastructure, so why we put the hydrogen through there? And as you can see from this article in the Telegraph, there are big ambitions to do it as soon as this year. So this is a bit of an old article from a couple of years ago. And because of their lack of understanding of, what's going to happen in terms of fracture, we actually postpone this. It's not going to anymore happen in 2025. It's going to be maybe next year, hopefully. But the idea is that, okay, can we transport hydrogen through these pipes? And that's a challenge because, well, we know, first of all, hydrogen makes those pipes brittle. Those are metallic pipes. Those gas pipelines have been installed there over decades. So they are very different types and shapes. They're using different materials. They have been welded in different ways. They have undergone corrosion. So they have very different types of defects. There's also multiple options, quasi-infinite options. You can transport hydrogen, pure hydrogen gas. You can blend it with other gases. You can transport hydrogen at any pressure that you wish. The higher the pressure, the more hydrogen you can transport, and so on and so forth. So there's many questions that are difficult to answer, both from a scientific point of view, but also from an engineering point of view. And these are very pressing questions. We need an answer tomorrow, if not today. So what we're trying in my group is to try to answer those questions. We do a lot of experiments to answer those questions. But I won't talk about the experiments today because some of these questions are actually quite difficult to answer experimentally. Again, there's a quasi-infinite combination of materials, well conditions, defects, possibilities in terms of hydrogen pressure and purity that relate to this natural gas pipeline hydrogen transport, or the proportion of natural gas for hydrogen transport. So it's very difficult to test all these conditions in the lab. Also, we know, for example, that the weakest links are the wells, that they have residual stresses. It's very difficult to extract sufficient amount of material in the hard, brittle regions of the well that we can test in our labs. So there's a revolution now going, an opportunity to use numerical models to predict what's going to happen. So this is the idea. Can we do experiments that reveal new scientific understanding? And once we gain that fundamental understanding, can we build on the growth of computers to develop a new class of mechanistic models that will very reliably tell us what's going to happen? And these models need to be physically based and reliable, because we don't have a second chance. We need to handle, we need to tell these people whether it's going to be, under which conditions it's safe to transport hydrogen in natural gas pipelines. So we don't have a possibility of recalibrating things, of doing experiments, and so on. We need to be as reliable as we can be. And we can be reliable if we resolve the physics of the problem. So the philosophy here is to maximize the physics and remove empiricism. We don't want any phenomenological laws. We don't want parameters that we calibrate to an experiment and we don't understand very well what they mean, and alpha, beta. We want models that basically resolve the underlying physical processes as if they were happening in reality. And in that way, we minimize assumptions and we deliver predictions that are based on fundamental physical constants, material properties that I can measure independently in my lab. And this is possible now because computers are big. They're big enough that we can finally kind of solve this by brute force. We can solve all the things that are happening in your problem. And basically, if you want to understand how those pipes will transport hydrogen, you need to resolve the multiple stages involved in this hydrogen embrittlement process. One is, how much hydrogen enters your metal for a given environment. The other one is, what is the hydrogen doing within the metal, how it diffuses through the metal, how it interacts with defects that exist in the metal. And then finally, the embrittlement process per se. How does hydrogen nucleate cracks? And how does it make easier for those cracks to grow? And I won't bother you too much with the details, but just in case someone was interested in the technical details, I include a few equations. We do have models that you solve with finite elements. You've seen finite elements as part of your undergrad here at Oxford or elsewhere. And the good thing is that now our models are big enough that we can resolve these physical processes, again, by brute force. And you can see here, for example, if you want to predict the hydrogen uptake, I won't get into details, but basically you saw, for example, these are the Nernst-Planck equations for electrochemical environments. Those of you that are familiar with chemistry will recognize these equations. So these are equations that you can see, they depend on parameters that we fully understand, right? This is diffusivity, this is Faraday's law, Faraday's constant, T is temperature, R is gas constant. So these are material properties that I can measure that have a unique meaning. I know the value of these things before I run any simulation. There's no calibration here whatsoever. So there's multiple processes involved in the uptake of hydrogen. It's an electrochemomechanical process, but we can solve this electrochemomechanical process now. Once we do that, then you get a finite element model, and then you get something like this here. You can see here, for example, this is an electrolyte. You have a crack. Here is the metal, and you can see the distribution of the electrolyte. And this is very useful because engineers, normally they can do measurements here, but we know that when you have defects, situations are going to change quite dramatically, as you can see here. So it's important with these models, we can tell, from your measurement there, what are the conditions in the regime that you're interested in. But that's the idea. We have now finally reliable models that depend on material properties that we can independently measure that can tell us how much hydrogen is coming into our metal. And this is also useful for hydrogen production because we're resolving these hydrogen evolution reactions that the people in the hydrogen production, so electrolyzers and so on, are interested in. And then once you know how much hydrogen is in your metal, you have a concentration here. You want to figure out what is the distribution of hydrogen within your engineering component as a function of time, and also within the microstructure of your metal, because that's going to tell you whether fractures are going to initiate or not. Hydrogen not only travels freely through the crystal lattice of your metal, it's also what we call trapped, sequestered at specific locations, specific defects, such as grain boundaries, dislocations, carbides, which is what we represent here. And we have, again, models for this. These are extended versions of Fick's law. You will remember Fick's law from any other transport model that you have done during your undergrad, and you will remember that this, again, is based on properties that we can measure: diffusivity, Again, temperature, this we know. There's some binding energy related to the defects. Everything we can measure independent on the lab. So again, by applying brute force, we finally have computer models that are big enough. We can solve all these interdisciplinary problems at the same time. And by the way, all of this, the coupling is quite strong. All of these phenomena are quite coupled. So this is a hydrostatic stress. So the deformation of your material is going to drive hydrogen concentration. So that's quite important. So it's a coupled problem, but if you can do clever experiments to resolve those couplings, then you can solve with computers all the equations that are describing those physical processes. And then when you do that, when you see something like you see here, so you can see, for example, distribution of hydrogen within this component. This is a pipeline. You can see we're increasing the pressure inside of the pipeline, so the hydrogen concentration increases, and the hydrogen diffuses within the pipeline from the maximum in the inside to the minimum in the outside. And here you can see a different component, it has a defect, and so on and so forth. So once you have, you know, the PDEs that are solving your problem, you did the experiment, you have the material properties that drive those PDEs, you implement this into a finite element problem, and you can quantify what is the distribution of hydrogen within your component. And then finally is the embrittlement process. How does hydrogen trigger cracks? Again, we have equations for this. These are more on the mechanics side of things. And you can see here, basically, we capture revolution. This is something called facial models of fracture. And you can capture how hydrogen basically reduces the toughness of your material. And you can connect this with atomistic simulations that tell you, without any fitting parameters, what is the reduction in fracture energy that you get from adding hydrogen atoms to your metallic system. And when you do that, basically, you can predict the nucleation and growth of cracks. So here in red, this is a crack. You can see this is what we call a compact tension sample. We're applying a load, and you can see that the crack is growing. This is a cyclic load. This is fatigue loading. You can see that the crack is growing, accelerated by the presence of hydrogen. This is another geometry. And any geometry that you're interested in, you can simulate it. And these models have proven to work out very well. You can see some various calculations here, some representative results, and comparisons with experiments. You can see here, again, those models have no fitting whatsoever. All the parameters we know before we run a simulation. And you can see these are experiments on notch tensile strength steels, high-strength steels that were pre-exposed to hydrogen. The symbols of experiments, the line is the prediction for the model, a very good agreement for over a wide range of hydrogen concentrations. These are those pipeline steels that I showed you before. These are called arc curves, crack growth resistant curves. And you can see that the model behaves very well in the absence of hydrogen. Then we expose that pipeline to a 10 megapascal hydrogen pressure, a typical value that is being considered, and we get, again, a very good agreement. This is fatigue cyclic loading. And you can also deal with the microstructure. You can deal with, lab samples, and you can scale things up. You can also simulate with these models real complex engineering problems. So for example, here we are simulating the welding process. This allows us to predict much more precisely what is the distribution of properties within the weld, residual stresses. You can see that we can solve some nasty problems. This is a pipeline that contains, let's see if it runs, that contains hundreds of defects due to pitting corrosion. Those defects are going to grow driven by hydrogen. You can see how those defects are growing at the top, merging with each other, and eventually you get the complete failure of the pipeline. And we have compared our predictions not only with lab academic experiments, but also with real full-scale experiments. These are pressure vessels, and you can see that we can capture the number of cycles to failure quite nicely. So this is an opportunity because these models, again, not only brings us new physical insight, but this idea of virtual testing that we use quite significantly in automotive and aeronautical industries, we can bring it to hydrogen-containing environments for energy and other applications. So that's the promise, basically. And along the same lines is the battery problem. So I think you're all familiar how batteries work. So whenever you charge your battery, you have lithium ions going from the cathode into the anode. Whenever you discharge the battery, you have lithium ions going from the anode to the cathode, and then you have electrons in the other way around. And basically, because of this, when these lithium ions go from one place to the other, they get stored in these cathode or anode particles, and this brings a lithiation process. So they accumulate this lithium, and therefore they swell and shrink. And every time you charge and discharge your battery, you swell and shrink your particles, and that leads to the initiation of cracks, as you can see in this microscope image. And this is the reason why we need to change our laptops, our phones every 2-3 years, because the battery is degrading, because we have these cracks appearing as a result of this charge and discharge, these lithium atoms going in and out of those particles. So we thought, okay, we have developed multi-physics models that can capture the formation, diffusion, fracture. So why not apply the same ideas to batteries? And this is what you can see here. This is an example of one of these particles. And this is going to say the equations for those of you working on this area, they are very similar to the hydrogen ones. That's why we can tackle multiple problems at the same time. It's not that we're very clever. It's just, it happens that the tools are very universal. And you can see, so you solve a displacement problem. This is basically the standard balance of linear momentum that you were seeing during your undergrad. Then there's an equation for the evolution of the fracture, which again, it uses one of these facial methods that have been a revolution in fracture mechanics, and basically compare the stored energy in your material to the fracture energy. This is the Griffith criteria that you learn about during your undergrad. And then the transport problem. Before it was hydrogen, now it's lithium. Again, similar problem. And different to the hydrogen problem, the lithium causes chemical strengths. Hydrogen also causes chemical strengths, but they're small. They're very small because this partial molar volume is quite small. It's an order of magnitude larger in lithium. But as you can see, all of these things rely on physical properties that we understand, that we can measure, and therefore phenomena come naturally. We don't need to make any big assumptions. And again, we have implemented these models. This is in collaboration with, I forgot to say that, of course, this is work in collaboration with many people across the UK and the world. This is in particular work done with my good friend Adam Boyce and Paul Shearing, who's also at Oxford, the director of the Zero Institute. And we look at the nucleation of cracks and the cyclic load in realistic particles. We also went down the scales to resolve the microstructure of those particles. So people say, Tesla is proposing this million cycle battery where they're going to use a single crystal. So you remove those green boundaries that are the weakest link. We can test those ideas into our model. And again, similar to hydrogen, our goal here is to develop virtual platforms that allow you to map safe regimes of operation and also test ideas, test new solutions to battery durability problems, hydrogen transfer problems. And it's very efficient and cheap to do when you have a reliable model because you can test quick. Some of these experiments, particularly in hydrogen, are very, very expensive. You can do those things very cheaply, very quickly with these models, and they are reliable. And then we have also looked into full battery electrodes, and again, also for solid-state batteries, I did not include here, but also in solid-state batteries. But the idea, again, the same. Can we map regimes where we can use these things safely so we don't need to rely on big safety factors? We can tell people, which battery technology is going to work in which application. And then also, can we test ideas quickly? Can we say, okay, what happens if you remove the microstructure? How many cycles to failure do you gain? And so on and so forth. And let me just finish with a couple of slides about wind energy. This is another area that we're very interested in. Richard, who introduced the webinar today, is also very active in this area, and a lot of other Oxford academics are. Again, the progress has been impressive. However, as I said before, we need to bring this down. We cannot stagnate here. We need to keep bringing this down if we really want to commit, or if we want to achieve those commitments that the UK government and other governments have put in front of us. And one area where I think we can win a lot here is the life cycle management of this wind energy offshore farms. And because it's still in its infancy, and there's a good reason for it. It's a new technology, but you can see the lifespan of offshore wind turbines is 25 years. This is very small. This is very short. This is shorter than nuclear power plants with all the challenges that come with nuclear power and their safety. And operation and maintenance costs are 80% of investment costs. So I think there's a lot we can do here. And of course, this is only natural because, it is a new technology, so we're trying to understand what happens. And there's a very good opportunity in front of us because what you see there is Hornsrev 1. This is the oldest large-scale offshore wind farm in the world. This is operated and managed by Vattenfall. And we're working with Vattenfall to try to make an educated life extension decision. Do they need to replace these things after 25 years, or will it last 30, 35, or 40 years? And at this point, you may wonder, okay, Emilio, how do they come with this 25-year number? So it's very simple. What they do is they do SN curves. You may remember that from your undergrad degree. So they do uniaxial tension curves, tension tests, and there are multiple cycles. So they take a piece of metal, they load them to multiple cycles, and they're given the stress amplitude until it breaks, and that gives them a point in this stress amplitude versus number of cycles to failure graph. Then they do another test at a different load amplitude, another one, and so on. And eventually they have enough data points that they can draw an SN curve. So then they say, okay, now we know, I look at my wind turbine, I can take into account the loads from the fluid, from the sea currents, from the wind, from the waves. And then I determine this is my stress amplitude of 50 megapascals. I go into my graph, I go down here and I figure out that it's 10 to 7 cycles to failure. So then I say, okay, if the frequency of loading is 1 cycle every 7 seconds, that gives me 125 years of operating lifetime. So what happens when you have corrosion? Well, we don't really know what happens when you have corrosion. So what the industry does is they bring this curve down by a safety factor. They apply a knockdown factor that is magic number 3, which is based a little bit on the oil and gas experience, which is very different conditions, very different structures, very different amplitudes. But anyway, we needed to, it's a new technology. We need to do something. Engineers cannot just sit on their desk. They need to do something. And then when you do that, basically you do the same process. It's 50 megapascals. You go down here, you get this number, and then you get 25 years. So of course, there's a lot of questions about this, and this might not also be the best technology to figure out what is the life in corrosion fatigue, because there's no time dependency here, and corrosion is a time-dependent process. We're talking about a constant load amplitude. Again, there's a history dependence, and we cannot anymore apply superposition because we have corrosion that is a nonlinear history-dependent problem. So there's many caveats with this. So what we're trying to do is, again, bring this idea that maybe we can develop models that are mechanistic, that explicitly resolve the underlying physical processes, and therefore allows us to predict what's going to happen. And the reason why these wind turbines only last 25 years is corrosion fatigue. So is the fact that you have a monopile, a metallic monopile, a carbon steel, a structural steel in a very aggressive environment, a seawater environment. That generates speeds. Those speeds are going to grow, driven by local chemistry and mechanics. And eventually you get the speed to crack transition and the propagation of a crack. And this is a very nasty problem because, there's chemistry, there's material science, there's mechanics, there's structural mechanics, and so on and so forth. And I mean, it's corrosion, right? Corrosion is a kind of one of the biggest long-standing problems for scientists and engineers. And only in the UK, it accounts for a cost of £46 billion. And it's really an elusive challenge for us, and one that has eluded computer simulation. So when you talk to my experimental colleagues, they tell, corrosion is a too complicated problem to solve with computers. But we're trying to do that. And the beauty of this is that we actually understand very well through decades of corrosion research what are the mechanisms of what is happening. Yes, that's true. Corrosion is very complex. There's many things happening in corrosion, but we know what is happening. We know what are the differential equations that describe each of these phenomena. And we finally have the computer power to solve all these things at the same time. So we can solve things as they happen. And we also have, by the way, technologies to simulate how interfaces evolve. This is these so-called facial methods. So you can see some representative examples here. We developed this new class of electrochemomechanical facial corrosion models that allows us to predict how the corrosion front, the blue part, the seawater, evolves as a function of the metal. You can see here how the corrosion front goes across some insoluble secondary particles. You can see how the corrosion front evolves through grain boundaries. Here you can see how the electrochemistry of that corrosion front is changing as a function of the shape of your defect. Here you account for the microstructure. Again, in very good agreement with experiments, because when you bring the physics in, you get good agreement with experiments, again, both in the morphology and the degree of corrosion, and so on and so forth. So I think I'm exceeding my time for a minute, so I'm going to wrap it up now. But I think the key takeaway is that, it's easy as a politician to say that we're going to achieve net zero in 2035 or in 2050, because it's maybe 40 years down the line, someone else have to take on that commitment. But it is going to be a challenge. It is going to be a gigantic technological challenge. I think engineers have done miracles when it comes to tackling the energy transition, and material degradation challenges are going to be one of the key issues holding back this green energy development. And I hope to have convinced you today that the work that we're doing at Oxford is really accelerating this transition by basically developing a new class of mechanistic, physically based models that are interdisciplinary and that take advantage of the growth of computers to resolve the physics of some of these problems. And I'm happy to say, as an engineer, that some of these models are being used now to store and transport hydrogen safely. So to make decisions on the transport of hydrogen through those pipelines, to design pressure vessels to store green hydrogen. They're also being used to develop a new class of solid-state batteries and predict battery degradation by the industry. And we are also being used by Vattenfall and others to make an educated decision on the life extension of the oldest offshore wind farm in the world. So that's all. Thank you very much for your attention and your patience. I hope this was at the right level, and I'm looking forward to your questions. Thank you.